right, now that we've talked about bones in general, we're going to take a really close look at how they're formed by looking at bone stem cells. Bones contain stem cells for both blood and bone. Stem cells are called osteoprogenitors. Osteoprogenitors have the ability to become one of three cells. They can become osteoblasts. Blasts are the builders. They secrete the bone matrix itself. Osteoblast cells are going to be in that tissue. They're going to start secreting the bone matrix, and it forms that hard calcified compact bone. Osteocytes are mature bone cells that maintain the matrix around it. It's actually an osteoblast that became buried in the calcified matrix. As it made all of the calcified area around it, it basically holed itself in. It's like you building a brick house around yourself and forgetting to put a door in. On the left, we can see how it's actually encased itself in the matrix that it is currently supporting. That osteocyte can't go anywhere. It's stuck inside of the bone. On the right, we can see two different osteocytes, both stuck inside of a little bitty space that they have around themselves in the bone. They do have all these long tendrils, though, that go out into the surrounding tissue, which is how they maintain the area of bone around themselves and also get nutrients. The third type is osteoclasts. Osteoclasts dissolve bone to release minerals. As they travel, they leave behind pits and trails where both minerals and organic phases of bone have been dissolved. So these guys will just travel along, and basically whatever they touch of that bone, they're able to dissolve it into the actual minerals, which are then released into the bloodstream in the body. Maybe you needed a little more calcium in your blood. We can increase the amount of osteoclasts that are traveling around, releasing the minerals, and really build that calcium supply back up. This picture shows us a close-up view of our bone anatomy. We learn a lot about this in lab, so after you go through your lab, this is going to look pretty familiar. We have lacunas, we have osteocytes, we have blood vessels that travel down through the middle, providing all the nutrients to our blood. There's some that go from the outside in to supply that spongy bone with a good supply of blood. This picture is a cross-section of a compact bone, so it does show us periosteum on the outside and the endosteum on the inside. In the middle is the compact bone. It's almost cement-like, formed out of these round osteons that travel up and down, and they're basically cemented together to provide you that strong support. The spongy bone is going to be formed out of trabeculae, which is a lattice of spongy rods, and spaces between them are filled with bone marrow. There are tiny rings within the trabeculae that are called the parallel lamella. These are composed of bone matrix, but they lack an osteon. So whereas we have the osteons and the cemented together structure of the compact bone, the spongy bone has all of these open spaces that we can fill up with bone marrow, have blood vessels traveling through. On your osteons, all of the blood supply comes from the center of the osteon. With the spongy bone, the trabeculae themselves are so thin and narrow that they don't have to do that. They can receive their blood from the outside. So your little tiny trapped osteocytes, they'll just have little openings out to the surrounding area where they can bring blood supplies in. This is a cross-section of one of the trabeculae in a spongy bone. You can see all of the individual rings, kind of like the rings of a tree. Our bone is being formed through a process called ossification, or osteogenesis. It is the formation and the development of bones. Your body will actually have a softer cell model that it will lay down first. Then it begins to ossify into bone. This softer cell model is present in a fetus. Pictured here is a 12-week-old fetus. The bones themselves are beginning to form, but they're not done. The red here is bone, and the area that is yellow is just where there's only cartilage. You can look at the fingers and see that only parts of the hand and the fingers have actually been developed as bone. Also in the legs, and most of the joints are not bone yet. A lot of this development will finish once the baby is born. There are two ways to ossify or form bones. Both of them start with the mesenchyme. Some bone goes straight from being mesenchyme to being bone. This happens inside of the membrane. The other strategy is for the mesenchyme cells to become hyaline cartilage, and then the hyaline cartilage converts into bone later on. Your body will use both of these methods. The inside membrane bone growth is called intramembraneous ossification. This is when the mesenchyme directly becomes the bone. Bones produced this way include your flat bones, some of your facial bones, your mandible, and the central part of your clavicle. All of those are formed by the mesenchyme itself going straight into bone.
Some have described the skeletal system as the infrastructure of the human body, providing a rigid framework that offers protection and support, as well as attachment sites for the tendons and muscles that are essential for locomotion. The skeletal system is comprised of 206 bones, each of which is formed through a process known as ossification. Bone development and remodeling takes place on a continual basis from the prenatal period and early childhood through adulthood, as well as during the healing process that occurs following bone fractures. Ossification can take one of two forms depending on the type of bone that is forming. In the case of flat bones, like those of the ribs, scapula, pelvis, and skull, the ossification process is known as intramembranous ossification. The process is initiated by mesenchymal stem cells, which are cells that have yet to be differentiated into a particular cell type. Eventually, centrally located mesenchymal cells within the embryonic fibrous connective tissue differentiate into bone-forming cells or osteoblasts. This process constitutes the formation of what are called ossification centers. In the matrix formation phase that follows, the osteoblasts begin to lay down osteoid, which is the organic part of the bone, consisting of collagen fibers. Some of the osteoblasts are entrapped within the osteoid and are then said to be osteocytes. The osteoid then calcifies and forms slender, needle-like structures of spongy bone called spicules, which aggregate in the form of small supporting beams or trabeculae. Meanwhile, the blood vessels on the outside of the spongy bone condense and form the periosteum, the fibrous sheath that covers bone. As the trabeculae thicken, an interconnected network forms, resulting in what's called woven bone, which is characterized by a somewhat haphazard organization of collagen fibers and is mechanically weak. Eventually, this leads to the formation of lamellar bone around the newly formed spongy bone. This lamellar or compact bone has regular parallel alignment of collagen in the form of sheets, or lamellae, and is mechanically quite strong.
This is the process that takes us from mesenchyme tissue to bone in one go. Here on the left, you're able to see that all of those little osteoblasts start to congregate together, form some bone. Two of them got trapped in the middle of the matrix that they created, and the other osteoblasts around them keep building a bone matrix. They increase, forming all of the trabeculae and the woven bone, and then eventually form the compact bone on the outside. This is one of the flat bones of the skull. Have you ever heard of a fontanelle? It's a soft spot felt on an infant's skull. Fibrous connective tissue is going to connect those developing flat bones. With babies, there's a slight dilemma. The head has to be able to come through the birth canal, but because of the rapid brain growth, it has to grow very quickly. Having the fibrous connective tissue in between those bones allows us a little bit of flexibility, and that way we can squeeze it a little more to come out and provide a little space for growth. So that would be a soft spot right on top where the fibrous connective tissue is connecting all of those ossified bones. It does eventually harden over. The other type of ossification is within the cartilage bone growth. The name here is endochondral ossification. This is where hyaline cartilage becomes bone. Most bones are going to be produced this way. Your long bones, your pelvis, your vertebrae, the ends of your clavicle. Now this bone growth takes some time. This newborn mouse has been dyed so that you can see the difference between the hyaline cartilage and the actual bone. Over time, a lot of that cartilage is going to be converted into bone.
While flat bones are formed through intramembranous ossification, most bones in the body, such as the long bones of the legs and arms, are formed in a somewhat different manner known as endochondral ossification. This type of bone development involves cartilage models, which are eventually replaced with bony tissue. The process begins in the developing fetus and can be divided into several stages. Around the 8th week of development, chondroblasts begin secreting a cartilaginous matrix that will form the hyaline cartilage model for bone development. As with other hyaline cartilage tissues, chondrocytes are trapped in lacunae and a perichondrium surrounds the model. The next stage begins when chondrocytes within the center of the model hypertrophy and begin to resorb some of the surrounding cartilage matrix. As these chondrocytes enlarge, the matrix begins to calcify and chondrocytes begin to die, as nutrients cannot diffuse through the newly formed calcified matrix. Next, stem cells within the perichondrium divide to form osteoblasts, and a compact bone collar is formed around the calcified cartilage shaft. A periosteal bud consisting of capillaries and osteoblasts invades the core of the cartilaginous shaft, forming a primary ossification center. The remains of the calcified cartilage serve as a template on which osteoblasts can build bone. Bone development extends toward the epiphyses from the primary ossification center. Most primary ossification centers are formed by the 12th week of development. The same basic process of primary ossification is repeated in the epiphyses as secondary ossification centers are formed, replacing the calcified cartilage with mostly spongy bone. As the secondary ossification centers are formed, osteoclasts resorb bone within the diaphysis, creating a hollow medullary cavity. When secondary ossification is complete, the cartilage is totally replaced by bone, except in two places. A region of cartilage remains over the surface of the epiphyses as the articular cartilage, and another area of cartilage remains between the epiphyses and diaphysis. This is known as the growth region or epiphyseal plate and is the point from which all growth in bone length occurs. At adulthood, epiphyseal cartilage plates are completely ossified and bone growth stops.
To summarize, in endochondral formation, the first step is a fetal hyaline cartilage model develops. In the fetus, this connective tissue holds the positioning of the bone. Second step is when the cartilage calcifies. The third step is the primary and secondary ossification centers form. This happens in the middle and the ends of the bones. The fourth step is that the bone replaces almost all cartilage. The fifth is when lengthwise growth continues until the epiphyseal plates ossify. There's a disease called osteogenesis imperfecta. This is a genetic bone disorder characterized by fragile bones that break easily, also called brittle bone disease. These pictures show us the different severities of this disease. Type 1 has about normal height, but their bones can break very easily. Type 1 females, as they get older, they start to have more breakage, they start to compress more. Type 4s, sometimes you'll have entire limbs that eventually have to be amputated or not there. And type 3s are very severe in that the bones themselves just don't provide that good supportive skeletal system because they're too weak. When you're born, just like that newborn mouse, you still have a lot of cartilage towards the ends of your bones. Your joints have not had the proximal and the distal epiphysis completely ossify yet. These x-rays show us the hands of different age groups. A male at 6 months has the bones that don't fully meet because there's hyaline cartilage between them. So you'll see these gaps basically. By 6 years old, we've seen a lot of development and the majority of those joints is ossified. By 8 years, then we're starting to see the complete ossification in the wrist. The bones almost meet, and it's almost complete at this point. Epiphyseal plates are present at the ends of your bones on the proximal and the distal side. When you take an x-ray, bone shows up as white, and cartilage and other soft tissue shows as black. On the left side, we can see that towards the proximal end, there is a black line going across this bone on both the top femur and the bottom tibia. This is called the growth plate, and it is where that lengthwise growth in the bone is happening. If you can see a visible line, they are called open growth plates. And after a certain age, they ossify and they become closed, and there's no black line visible. If you've watched forensic shows, you've probably seen them identify the age of a victim based on the bones, sometimes just 1 or 2. They're doing that by looking at the epiphyseal plates. Is it open? Is there a partial union? Or is there a complete union? On these 2 bones, they actually are the same bone, but with different ages. On the left, there's a partial union, so we're looking at someone who's probably 20s, maybe a little younger. And on the right, we see open. This could be someone who's 10, who's 8, much smaller. There are charts available that give us ages for when each of these unions happen. On the proximal side and on the distal side could be different by a couple of years. Doing this, we could take a male's radius bone, and just using that bone alone, if it had complete union of the proximal radius plate, which based on our chart happens between 14 to 19 years old, so they are a minimum of 14 years old, and there is a partial union of the distal radius plate, so it's not completely closed. The distal closes from 17 to 22 years old. So this is someone between the ages of 14 and 22, probably closer to that 18, 19, 20 years old. You're able to tell so much just by that one bone. Now, if both of the radius plates were open, we would have been looking at someone younger, and we could have used the overall size of the bone to estimate it. But if they were both closed, that's when it gets a little trickier because you know they're an adult, you know it's a male, but if both are closed, it can be a little harder to tell.